record. I see a text view recording and posting. Yeah, I'm starting. Okay. Share that thing again. So the first lab we would, okay, first of all, let's talk about the list here. Since it's a complicated system, so there are a lot of valves, just like when you operate a real industrial systems. So you have to follow the plan to follow the schedule to how to open and close and turn on and off. Okay, it's not like just pushing a button. There's so many valves you have to control to close and open to make sure it runs as you expected. Okay, so in the system we have 3 type of condensers there. 3 type. One is, condenser, right? Condenser is that's a heat exchanger, right? Okay, you use to cool the refrigerant. Okay, remove the heat from the refrigerant. So there are 3 condenser system there. You can run all together. You can run one of them. You can run 2 of them. That's why you have a lot of valves to open and close to make sure that's what you want to run. Okay, so they have a shell and tube heat exchanger. They have a tube and tube heat exchanger, and they have a air-cooled heat exchanger. Okay, so in the actually when you do the experiment, we turn on one of them. Okay, so at the time when we actually do the lab, 2 people group when you operate it, one group do the shell and tube heat exchangers, the other group do the tube and tube. So the operation will be different totally. Okay. So when you set it up, then you have to go through those valves. Each valve you have to, open and close, follow the schedule, okay, to make sure you go to the shell and tube or you go to the tube and tube heat exchanger. We're not running the air-cooled heat exchanger. So that's the procedure, okay. Oh, I haven't posted the safety handout yet. Have I? I haven't, right? In Moodle. I need to. Okay, I give you time to prepare for it. I post this week and take a look. We will probably have safety quiz later. Okay, a couple weeks later, maybe. Maybe the next time we have a lecture, we will do the safety quiz. Okay. So this is the operation. So you're an engineer, right? You need to know how to operate. In case the technician goes strike, you guys are the one to operate it. Okay, so that experiment actually a lot of hands-on, a lot of operation in there. So actually it's a good experiment. But now the goal of this, there are 2 goals for this lab. Okay, one is to produce the pH diagram. All the cycles have the diagrams, right? Refrigeration cycle, you have two types of diagrams. One is what? pH diagram. What is the other one? Anybody? Forgot? You had 2 thermals, right? You should be good. You should be better than me on thermals. I'm not teaching thermal. Okay. What is the other one? pH diagram. Forgot? What is pH diagram, first of all? pH, P is pressure. See, here's the diagram, empty blank diagram, right? Pressure versus enthalpy, right? That's called pH diagram, right? Enthalpy usually use H to represent it, right? So in the refrigeration cycle, what's the other one?
Is it a TS?
Yes, that's a TS, right? Yeah. I assume everybody knows. Okay, so let me switch my screen again. Let me turn on my whiteboard. I need to write down something more detail. Okay. See, it's okay for me to do either one. If I ask you to do either one, either pH diagram or TS diagram, both of them are important. Okay, so let me give you what it look like in one diagram. You probably need to figure out the other one. Okay, measure the diagrams. Okay, for the refrigeration cycle. Okay, so that's the goal. One of the goals. There are 2 goals later. I'll I'll tell you the other one. Okay, so now let's do a review for the refrigeration cycle. You had two thermodynamic class. You should be good on this. Okay, so let me ask you this: how many components, major components for a refrigeration cycle?
4.
4. What are the 4s? Four, right? It's correct. It's 4. Tell me more.
Valve,
Okay, valve. What do you call it?
expansion valve.
The expansion valve. I draw a valve here. Okay, this is the expansion valve, right? Okay, what are the other 3?
Compressor,
Which one is the compressor? Can you tell me?
the one across from the expansion valve.
Okay. Compressor. Good job. Anything else?
Okay, somebody else's turn.
Okay.
The condenser.
Condenser, top or bottom? Oh, depend on the flow direction. Okay,
Yeah,
that
well,
question.
depends on which way it goes, but
Okay, so tell me what the direction and which one. You said top. Okay, condenser, it's fine.
yeah. So if it's top, then I guess it would be
Clockwise or counterclockwise?
can
The flow direction for the refrigerant.
clockwise, right?
Clockwise? So
No,
go
no.
condenser, then go compressor?
No. Yeah, the other way, counterclockwise.
Counterclockwise, right? Okay, so what is the last one?
Is it an evaporator?
Evaporate. Of course, you need the you need the cool air, right? You're exposed to the evaporator, basically, right? Okay, so tell me a little bit more about the cycle. Which parts are the heat transfers? Which 2 parts are doing heat transfer? And which one part is the work?
The compressor is the work.
Work in or work out?
Work in.
Yeah. W in, right? Okay. Which parts are the heat transfers?
Condenser and the evaporator.
Okay. Which one is the heat transfer in? Which one is heat transfer out?
Out is the condenser, and then in is the evaporator.
Yeah, exactly, right? Q in. And they remove the heat, right? From the refrigerant. Q in and Q out. Okay, so that's a system, right? So TS diagram. Okay, anybody remember? I'll give you a TS diagram. You probably need to figure out the pH, okay, from the measurement. You have a dome, right? TS. Okay, let's say state 1, point 1, point 2, point 3, and the point 4. Okay, let's look at point 2 to 3 first. Okay, what's the state of refrigerant in point 2? Is it liquid or vapor or mixture? So because you need to draw the diagram, you need to know the dome, inside the dome or outside here or in here, right? Vapor is here, right? In the right. Liquid, right, is in the left. Inside the dome is mixture, right? Is that what we learned in thermal? Okay, I never taught some thermal, so I don't actually know what you learned. Everybody remember this, right?
That's what they teach.
Yep.
Yeah, good. Okay, so state 2, let's say you have point 2. At point 2, what's the state of refrigerant? Is that vapor, liquid, or mixture?
2 is a mixture.
To the mixture. So what you said is it should be inside the dome, right?
Yes.
Okay, this is a 2. What happened between 2 to 3? You have heat transfer in,
Yep.
heat in.
After it goes through the evaporator, it's going to become a vapor.
Ideally, it should be on the line, right? Saturated vapor, is that right? So let me ask you this. So I need to draw the 2 points here. Is the temperature changing when you go through 2 to 3, go through the evaporator? Is temperature increase or decrease?
It's supposed to stay the
Yeah.
same.
Supposed to stay.
Because that's phase change, right? Your heat is used to change the phase from mixture to vapor. So the temperature won't increase, right? Is that right? Okay, so the temperature will be the same between 2 and 3. And the 3 should be on the saturation line, on the dome line. Okay, so that's saturated vapor. Okay, here. Then goes through the compressor. What happens then? Temperature. Well, now you have walking, right? What happened to the temperature? Now it's a vapor. You pressurize it basically.
Temperature increases.
Increase. How about entropy? Acid entropy, right? You know, ideally, we're talking about ideally, right? Isentropic, right? That's called, right? So between 3 to 4, ideally
The entropy would stay the same, hopefully.
stay the same, right? Yeah. Okay. Then that's 4. So what's the state of refrigerant at 4? Superheated, right? Superheated vapor. It's inside the vapor region, definitely. Okay. So 4 to 1, what happened? Now you have very hot vapor here. Then you have to cool it down, right? Use the condenser, okay? Condenser to cool it down. Then at the end, after go through the condenser, what's the state at 1? You remove heat, cool it down.
Yep.
Then it become, well, it will go through this process, right? Reach
Saturated.
the
liquid.
dome, then keep decreasing entropy, and then on the saturated line again, it's saturated liquid, right?
Yeah.
This is a review, right? Then you just connect 1 and 2, because then you have expansion, right? It's not straight. Entropy changed. Okay. And the expansion, you didn't do anything. You just expanded. Okay. When you expanded, then the liquid become a mixture. Okay. Okay. Then temperature obviously decreases. You want the refrigerant, right? To refrigerate system to cool your outside temperature. So from 1 to 2, then the temperature drops to reach to the favorable temperature. Okay, but it becomes mixture. So this is a cycle, TS diagram. So I want you to produce a pH diagram. Okay, pH diagram. Also the dome, right? So let me ask you this: entropy, pressure. How does the pressure and enthalpy changes between 1, 2, 3, and 4? Okay, so between 2 and 3. Okay, 2 again is inside the dome, right? What happened to the pressure? Between 2 and 3, 2 to 3. You're receiving heat. You receive heat, right? So what happened to pressure when you just heat it up?
Increases.
Hmm?
It
Decreases?
increases.
Increases or decreases? Anybody else? Everybody agree? Well, you have a cup of...
It's a decrease.
It's decreasing? You see, you have a pipe of water. You heat it up, then the water is still flowing, okay? Do you think the heat will increase the pressure much? your pressure, you have to put in a pump, a compressor, those kind of things. The pressure
I
would
thought
change.
the pressure in the heat exchanger was gonna be the same.
That's right. You just receive some hot temperature. It won't increase your pressure, right? Okay. So the pressure should be the same going through the evaporator, although the phase changes. Okay, on the saturated line. Okay. Then what happened between 3 to 4 for the pressure? It's compressor. Come on. Oh, so obvious. The pressure gonna
Now
change.
it increases.
Right? And your entropy gonna increase too. Okay. And what happened between 4 to 1?
This pressure is the same again.
Yes, it's a condenser. It's a heat exchanger again. Okay. Pressure gonna be the same again. Of course, the entropy decreases, and then you reach to 1. Okay. So what about 1 to 4? The pressure decreases, right? Obviously, you have to connect them. How about the entropy? That's a critical question here.
The enthalpy stays the same.
Entropy stays the same. Okay, it's expansion. It just expanded. Entropy won't change. Okay, it's critical in the measurement because in the measurement, the refrigeration system, you will do the measurement. It doesn't have all the sensors, pressure gauges on all the location 1, 2, 3, 4. You only have 2 pressure gauges. Okay, you only have 2. Okay, but does that enough? Okay, based on this, you should know it's enough. You have 2 pressures, that's it. And the key is between 1 and 2 here, it has to be a straight line going down. So if you know 2, for example, if you know 2, you should be figure out 1 without even doing any measurement, without doing any reading. Because the enthalpy is the same, it just goes straight up vertically. And then when you reach to the dome, that's the 0.1. Okay, so you have very limited data on the system. Okay, also in reality, you don't measure pressure everywhere to get understand the system. Okay, there's only 2 pressure in the system. Okay, that's enough. And between the expansion valve before and after, they have the same enthalpy. You don't need to calculate the enthalpy for both of them. You calculate 1, then that's it. Okay. Okay. So this is the review purpose. I think, is that clear? Clear to everybody for the refrigeration cycle? That's the bone, okay? That's basically key informations for any refrigeration system. I feel I'm trying to serve a review purpose here, okay? So for everybody fully understand the refrigeration system. You can actually do the repair work, do some measurement in your home residential refrigeration system, same, okay? Then you don't need to pay hundreds of dollars to find those technicians to do it. You're an engineer, right? You should do a better job. Okay, so now come back to, this is just a review for the content theory on the lab 1. So I want you to produce, based on the reading on the video, okay, you produce this pH diagram. Okay, then the second thing is, okay, oh, by the way, in the experiment, there's only pressure and the temperature reading. Okay, on the unit, there's no enthalpy meter or something like that. No, okay, you don't need to. Only pressure and temperature. Okay, can you find the enthalpy based on the pressure and the temperature? That's a task for you. Okay, okay, so you will see the video. In the video, you will read the pressure and temperature. You need to calculate the enthalpy. Okay, now the second question here is, I want you to calculate the degree of superheat at 0.3 at the evaporator outlet or at the compressor inlet. Okay, the drawing here is the ideal situation. Okay, ideally, after go through the evaporator, the point is on the saturated line. But in reality, when you do the measurement, you will find that actually it's not exactly on the line. It's a little bit inside the line here. Actually, they have dryer also in the unit system. So when you measure the point at the compressor inlet, and it's actually inside the vapor region. Okay, the point, actual point is from your measurement, the 0.3 is inside the vapor region. So I want you to calculate the degree of overheat at this 0.3, at the compressor inlet. So how do you find the degree of overheat? It's degree of superheat, right? It's not called overheat, okay? So it's easy. Okay, you actually have a line, connected the line inside to here, to actually the point. On this pH diagram, you look at the pH diagram, there are temperature lines. So this point actually indicates a temperature, right? There's a temperature line across this point. So you know what is the actual temperature here, or you just measured, okay? But if ideal case, this line is on the dome, this point is on the dome, there's also a temperature associated with that point on the dome, on the saturated line. So the difference between these two temperatures, the real temperature and the ideal temperature, that's called degree of superheat. Okay, so that's piece of cake to you after you actually produce this pH diagram. You just look at the diagram. Now let me come back to my screen. Stop sharing here. Come back to the handout. Okay, I provide you this empty blank diagram. Okay, use this diagram. Use this diagram. Okay, I don't want you to produce a new diagram for yourself. Just draw. You can draw it in computer, right? Cell phone or whatever. You can actually draw in there. Okay, or you can just print it. You draw on it. You use a color pen, maybe red color. Okay, blue color. Draw your diagram there. Okay. Okay, I cannot draw it on this, but you draw your diagram and place this diagram you draw with your pH diagram on it and place that in your report. Copy and paste it in your report. Okay, I don't want you to create your own, just use this. Then you can look at the actual 0.3 inside the superheat region. You see the temperature line there? Each line is a different temperature line. You have a temperature associated with that point, or it's just the temperature you measured, okay? I actually forget, that's the point you measure temperature? Probably not, okay? Then comparing to this line, you draw a line between 2 to 3, then across the dome, across the saturated line. Then saturated line, on the saturated line, there's also a temperature associated with it. So the difference between two temperature, it's your superheat, the degree of superheat, okay, at this point. So these are the two outcomes. Yeah, I think I wrote it down here. Measure the pressure, temperature at the various point, produce the pH diagram of the refrigeration system, and utilize the pH diagram to find the degree of overheat at the evaporator outlet. Okay, so these are the two requirements. Okay, then work on the calculation and do the report and do some discussion. Don't forget to do some discussion on your report. Okay, so this is lab 1. Is there any question? Okay, I see some of you put some text in the chat room. Oh, okay, you answered the question. Good. Yeah. Okay. Is that clear? Okay. Good. So the next lab will be much more complicated. Oh, okay. Oh, okay. I stop sharing. Go back to, okay. Now let me open the second lab handout. Okay, second lab, we are going to look at a specific component in this refrigeration system. Okay, we are going to look at what do we need to submit on the attendance? I see one of you asked a question. Oh, it doesn't matter. You just write your name. Okay, put something in the comment area, so I can just count you attended. Okay. share my screen again. Second lab. Second lab, we are going to, okay, now we are going to look at the condenser. Okay, as I mentioned earlier, in the condenser, you have the heat transfer out, right? Let me share my whiteboard again. Heat transfer out. Okay, so there is an energy balance in the heat exchanger. It's a condenser, it's a heat exchanger, right? When you do heat exchanger, you always study the energy balance between the two fluids. Okay, so for the condenser, the energy in equals to energy out. Is that right? Okay, what is the energy in? That's you see, this is okay. There's a refrigerant going into it and leaving it. Okay, so for the refrigerant, the heat is removed by the cooling water, right? Heat exchanger, you have cooling water. So that's the energy balance, right? So no, yeah, I should say this: delta energy in the refrigerant will be the delta energy in the water, which is the cooling fluid. Okay, so this is the energy balance. How much energy loss in the refrigerant will be equals to how much energy gain in the water. That makes sense? So we're going to utilize this equation to calculate the mass flow rate of the refrigerant. Okay, so in this entire unit, there's no measurement for the mass flow rate of the refrigerant. Okay, you don't need to. In any equipment, probably in your refrigeration system, you probably don't need a sensor to measure mass flow. Mass flow is difficult to measure anyway. You're gonna phase change or kind of stuff happen in there. It's difficult to measure. So they usually don't, but you should be able to calculate the mass flow rate easily. Okay, use this balance. Okay, so what is the energy change in the refrigerant before and after the condenser? Left-hand side of the equation is mass flow rate of the refrigerant. See, our unknown is there, right? Times what? Anybody remember?
The enthalpy.
The delta enthalpy, the enthalpy change before and after. Okay, so what number we use? One, state one here, right? After the condenser, state 4 before the condenser. So it's enthalpy at 1 minus enthalpy at the 4. That's the energy loss. Okay. Well, you can use 4 minus 1, right? You can have the positive value because loss will be negative. Loss is not equal to the okay, so you better change the sign. So what about this is a loss. How about this? You can do the absolute value of this, okay? Equals how to calculate the energy gain in the water side. Water is easier. You don't need the enthalpy, right? Mass flow rate of water times what? C times delta T. That's for water side, okay? Okay, so this is the equation you are going to use. I guess you probably, for the sign to be good, how about this? 4 minus 1, otherwise it's a negative, okay? So this is our goal, okay? So you need to know everything else, measure everything else, or get everything else in order to calculate this mass flow rate of refrigerant? Do you know everything else? You obviously have this based on the, you also already did it in the first lab. You need all the H's for the pH diagram. So it should be a piece of cake for you. And now just looking to the table or whatever value, you should be able to find this 2 H's. Okay, based on the measurement, temperature and the pressure. Okay. Water flow rate is shown on the, is that the panel showing water flow rates on the system. Okay. But let me tell you this: the water flow rate changes, fluctuates. It's automatic control by the system, depend on the temperature fluctuation inside the condenser. It automatically adjusts the flow rates, water flow rates. It fluctuates a little bit. So when you do the lab, do multiple readings and get an average. Okay. C is a piece of cake. It's a property, right? You should be able to find it for water. Okay. Delta T you need to measure. Okay. The water going into the condenser is a room temperature water, just tap water. Okay. In the experiment, I measured for you tap water temperature, about 76-ish Fahrenheit. Okay. The outlet water temperature need to be measured. I think I measured it for you too. Okay. It also fluctuates a little bit, but not much. Okay, so you should get the delta T. Okay, one thing I want to emphasize is be careful when it's a balance. This is a energy balance, instantaneous balance. So if temperature changes a little bit, then you have to exactly on the same time measure everything. Then on any given moment, the equation equals. Okay, if you measure this value 5 minutes before the other value, then they're not equal anymore. It fluctuates all the times. Okay, so I guess in the video you will see, we'll quickly do the measurement at the same time. But in the reality, when you actually do the lab, I usually put at least 4 students in this lab, 2 groups together. Okay, so you can 1, 2, 3, boom, measure all the data at the same time. Okay. Okay, keep in mind in the watch the video, when you get the data from the video, also try to do as close as possible, okay, in time. And do some average, especially the water flow rates. It fluctuates quickly. So get like 5, 6 data and do an average. Okay, get all the readings, put it on the Excel spreadsheet and do all the calculations there and submit the spreadsheet too. Okay, this is number 2, but this is not the end of the story. This is one calculation is for the mass flow rate. It also asks you to calculate something else. Let me get to my handout. It also asks you to calculate a couple of things, characterize the refrigeration system. One is the compressor efficiency. It should be familiar to you, right? Yeah, you did this many times. I feel you should in Dr. Chandra's advanced thermal, for a refrigeration system, obviously you need to know the compressor efficiency. Okay, every system, you need to know that. So this is the equation. Okay, so notice this is a compressor. So this is between, okay, the index is, the subscription is 1 or 2 here between the compressor. It's okay, just follow the diagram. So it's ideal. 2s, okay, isentropic enthalpy at the 2, okay, at the compressor outlet, minus the entropy enthalpy and the compressor inlet, divided by the actual enthalpy at the outlet minus the enthalpy at the inlet. Okay, so that's the equation to use to calculate the compressor efficiency. But you will ask, hey, how do I know this ideal compressor outlet enthalpy? Okay, so see, look at this drawing. Look at that straight line, constant entropy line. So if you measure the 1, just follow this isentropic line and then reach to the top line between 2 to 3, then the intersection here is your ideal compressor outlet. Okay. Okay. This point 2 is the measured, the actual compressor outlet. Okay, that's why this efficiency has to be less than 1, right? So this one in the numerator always smaller than the denominator. Okay, so that's the compressor efficiency. Very important. Every refrigeration system, you need to know the compressor efficiency. Okay, this is the way. So you need to do the measurement between you at least. If you want to calculate the compressor efficiency, you need the measured pressure and temperature on 1 and 2 before and after the compressor. Okay, so to calculate that. The other parameter I want you to calculate is efficiency of the performance. It's the ratio of the heat transfer in, okay, over the compressor walk. Okay, so that's called a coefficient of performance. Measure the performance. Basically, it compares the evaporator to the compressor. Okay, so these are all energy forms. Q, and no matter what Q or W, whatever, these are the energy forms. So calculate the energy form. Basically, is mass flow rate times the delta H. Okay, here, since you are trying to find the ratio, the performance is the ratio. So mass flow rate is the same. So you can cancel between the numerator and the denominator. So it becomes a delta H ratio. Okay, so it's very clear on this drawing. Okay, how do you calculate these two coefficients along with the mass flow rate of the refrigerant? That's your task objectives for the lab number 2. Okay, so you should have all the information based on the videos. Okay, to calculate all these things. Is that good? Hey, these 2 labs basically, you know, most of the important information of a refrigeration cycle, we reviewed it, and then we do a hands-on experiment to measure it, right? Only thing we didn't touch much is evaporator. Okay, the air side heat transfer. We did have an experiment like this in the previous semesters, but I didn't have the video for that 3rd one. Okay, but I will try to. I will try to, if I can enter the ETA, I will try to do a measurement for that 3rd one. Then I'll let you do it later in the semester. Okay, so then we have a complete picture, complete understanding of the refrigeration cycle and the refrigeration unit. Okay, hopefully it's helpful. At least can be helpful for your, in case your home AC system breaks down, you at least know what's the problem. You know how to measure pressure, right? Inside the residential AC. It's easy to look at the technicians, what they do. Put a pressure gauge there. You can see the pressure readings. And then just the other thing is just temperature. Okay, just pressure and temperature at a couple points. You should be fully understand the whole system. Okay, does it work well or not? Okay, I guess that's it from what I want to say. So next 2 weeks, each week I will post a video, lab video. Okay, then you will have 1 week to complete the lab report. The due date will be the same time, the class time, the following week. Or maybe I put the midnight, the class day of the following week. Okay, give you a little bit more hours, more times to do it. Okay. Is that good?
Sounds good.
Do we
Okay.
need to submit the handout as if we were actually in the lab filling it out, or is it just the Excel and
Just the Excel. Ignore this handout on this handout. Ignore these forms, data forms on the handout. Just put everything you read in the Excel. Put a table there. That's the reading you read. Okay. Then do the calculation following that reading data. Okay. And submit the Excel with the report. Okay. So hey, good. If you don't have any question, have a nice rest of the day, and see you next week. Oh, no, not next week. Next week, we don't have the lecture. See you in 3 weeks. They will have another lecture, okay? After 2 weeks lab. Okay.
So you're gonna post the video later today?
I will post the video next week. This week, basically, this an hour meeting is it's about the time. This is a 1 hour lab. So if you make a lecture, I don't want you spend more than an hour. So I post the video next class time. Okay, so 2 o'clock next Monday. So you will have 1 week to do that lab report.
Dr. Zhang,
Yes.
so just like in fluids lab, you're doing the same thing to as like the first week is just pretty much introduction, talking about it. But so like this week for fluids lab, we're gonna actually watch the video.
That's right.
Then
Fluids lab, we already had yes, we had the lecture last week. So I will post the video, the class time this week.
Right. Okay.
Okay.
Just wanted to be clear.
Yeah, that's the same.
Thank you.
You're welcome.
Have a good
Good.
evening.
You too. See you next. See you in. I see you guys a lot. You know, yeah, most of it in the capstone project. So, yeah. Okay. Later.